In the book of Psalms, it says, "The heavens are telling of the glory of God, and their expanse is declaring the work of His hands." Today on Origins, we're joined by a guest who shows us just how true that is, as we take a closer look at our solar system that surrounds us here on Earth, and we see how it declares the work of God's hands. Coming up next on Origins, we see an overview of the solar system with Dr. Jason Lisle. Hello, my friends, and welcome to Origins. My name is Donn Chapman, and it's my privilege to be your host. During this program, we showcased interesting guests who present evidence from science, along with other important facts validating the truth of creation and the accuracy of the Bible. Today's guest, Dr. Jason Lisle, has a PhD in astrophysics from the University of Colorado and is the author of Taking Back Astronomy: The Heavens Declare Creation. He was instrumental in the development of the Planetarium at the Creation Museum in Kentucky, and it currently works as Director of Research for the Institute for Creation Research in Dallas, Texas. Dr. Lisle, welcome to Origins.
Well, thanks. Appreciate it.
It's such a privilege to have you with us.
Well, thanks. Good to be on.
Now, what are we going to talk about today?
I thought we'd talk a bit about the solar system and how it declares God's glory.
Wonderful.
And just some of the things that you'd learn probably in a freshman level astronomy class, basically in college level class, and some of the things that I find very interesting, and how these things confirm biblical creation.
Catch some of us up. It's awesome.
Yeah. Well, you might know that the sun rises in the east and sets in the west. Most folks are taught that. Stars also do that, and that's because the Earth's rotating on its axis, and so everything seems to be going the opposite of the direction that we're going. But I thought we'd look at some of the other motions that we see in space, because you'll notice that the stars seem to maintain their same orientation relative to each other. The constellations don't change.
Right.
But there are a few stars that do, that seem to be moving, and these are planets. And there are 5 of these that are naked eye that you can easily see that sort of move around. So I thought we'd talk about how those move today, starting with our perspective on Earth and starting with one of the brightest objects we see in our nighttime sky, the moon. And so I have some software here that I'm going to use to actually show you some of these things. That makes it a little easier to understand how these things work.
Sounds exciting.
The moon is about the same size as the United States, just to give you a feel for it. If you'd put the U.S. at the same distance as the moon, it would cover the same area. And just to give you a feel for how large this object is, and it's 240,000 miles away, which is, it's a big distance, but you can kind of get your head around that, because some people have cars that have about that many miles on it. If you've got a really good car, you might get that kind of mileage out of it.
I'm
so you could have driven to the moon.
Yeah.
And the moon actually moves. And it moves through space in the same direction Earth is rotating, which means it seems to rise and set a little slower than the stars. Because see, it's working against the stars. The stars are all moving to the right, apparently, because of our rotation. And the moon is moving, relative to the stars, it's moving to the left. And so we can actually illustrate that here. And let me back up a little bit so you can see some of the stars. And you can see the moon is moving leftward, isn't it? Mm-hmm. And this is if you'd watch the moon over the course of time, and we're kind of hovering above the Earth right now, so we don't have to worry about the day-night cycle. And you can see the moon in its actual motion through space, and it goes through phases. Now, at the time that we're recording the show, the moon is actually in a full phase, and so that tells us that the sun is kind of back behind us, as it were, and so we're seeing the moon fully illuminated. But as the moon goes through its phases, you can see the sun illuminating different sides of the moon as we speed up time here. And you can see there, that's what we call a waning gibbous phase. And so you can see the moon is mostly illuminated on the left side, but there's a little bit on the right. And then as we go a little bit further, you see that's called third quarter phase, because the moon is 3/4 through its cycle. And that's a wonderful phase to observe the moon, because it's illuminated right down the side there, and you can see the shadows of those craters. And as we continue, you get a waning crescent phase. And then as we continue on, and after a while, you don't see the moon at all. And you might notice there's some times when you just don't see the moon, and that's new moon, because its cycles started over. And then as we continue, the new moon becomes a waxing crescent. Waxing means it's getting bigger. It's getting more illuminated.
And waning is smaller.
And waning is smaller, right. And so you can see when it's in the waxing phases, the moon is illuminated on its right right-hand side. And so that's how you can tell. And I like these phases where it's waxing because the moon's visible in the evening sky. It's following the sun. And you can tell that the sun must be to the right of the moon as we see it here. And that tells us that the moon is kind of, so it's going to follow the sun after sunset. So this would set shortly after the sun does. As we continue a little bit further along, you see the first quarter phase, and that's where it's illuminated kind of right down the middle. And this is the best phase to look at the moon because it's out at a nice time. The first quarter moon is at its highest point in the sky right when the sun is setting. And so that's the perfect time to look at it.
Yeah.
And and you can see it, and it looks so three-dimensional. When you look at the moon with a small telescope or even binoculars, your brain is able to figure out from the shadows of the craters that we're looking at a three-dimensional moon and not just a flat surface.
The craters help with that.
That's right.
Yeah.
It's amazing that the Lord has built into our mind the ability to perceive that kind of perspective.
Right.
You know. And as we continue along, you get into a waxing gibbous phase. Waxing means getting bigger. Gibbous means fat, and so the moon is actually gaining weight there, as it seems. And then finally we get back to the full phase where the moon is completely illuminated. And this is really, actually, this is the worst phase to look at the moon. That surprises people because you don't see any craters at all. It just because the sun is illuminating right down, and so there's no shadows. And so and it looks flat as a dime when it's in the full phase. You can't tell it's a sphere. So this is just kind of an overview of what you'd see if you'd watch the moon. It takes 1 month for that to happen.
You would think that the more light would make it more visible, but it's just the opposite.
It makes it brighter, certainly.
Sure, it's easier to find it, but it's harder to study it.
Yeah, it doesn't look as pretty when it's in that full phase, and because you don't see any of the shadows of the craters. So it's fun to watch this, and it takes 1 month for the moon to go through its phase, and that's where we get the word month. It's a month.
Yeah.
That's really where the word comes from. And of course, the Jewish calendar is all based on lunar cycles and things like that.
But it's not really like a 31-day month. It's like 28 days, right?
Yeah, it's closer to that.
Lunar calendar is all 28 days. Yeah.
Yeah, and so or 29 days, and depending on how the month is defined, there's more than one way to define it, but we'll maybe get into that a little bit later.
Okay.
Now, the moon actually is rotating. You might notice that we saw the same face of the moon at all times, and in fact, human beings always see this particular phase of this particular side of the moon, I should say. And that's because the moon actually does rotate. In fact, what we can do, we've been watching the moon from the Earth. And what I'm going to do instead, we can use this software to actually go to the moon.
Oh, wow.
And if we do that, we get a little bit of a different perspective. So now we're actually traveling to the moon, and I'm going to watch it from, this is like if I were just hovering over the surface of the moon. This is what we would see. And you can see the moon does rotate, actually, as we speed up time here. There it's rotating.
Yeah.
It's just that it keeps the same face pointed at the Earth. So as it moves around the Earth.
So as it rotates and we're rotating, we always see the same part.
In fact, there you can see the Earth in the background there.
Okay.
You can see the moon's keeping its same face pointed at the Earth. Isn't that lovely?
Isn't that amazing?
And if I follow the moon around, you can see that the moon keeps that same side pointed at the Earth, approximately. I always thought that would be just fascinating to see. Now, it moves a little bit because the orbit of the moon is not a perfect circle, and so it actually speeds up a little bit and then slows down. And so the Earth will, if you were standing on the moon, the Earth would stay in roughly the same spot in the sky.
Sure.
The stars would rise and set, the Earth would stay right there. It would wobble a little bit, and we can see that wobbling here as I go through it. And you can see the Earth, it goes through phases as well. And it's actually going through the same, if we were back behind the moon, the Earth would be in about the same phase that the moon would be in. So there's a waxing crescent Earth, and there's a first quarter Earth.
Wow.
Of course, the Earth is spinning, and it's spinning at a faster rate. It doesn't keep the same face pointed at the moon.
I've never thought about that perspective before.
Yeah,
That's
but
awesome.
this is kind of what the astronauts would have seen. Of course, they're on the other side of the moon, but they're looking up, seeing the Earth. And I've always thought that would be just marvelous, to stand on the surface of the moon and look up and see the Earth, knowing everyone you know and have ever known had lived on that little blue ball. It's quite stunning. And of course, the Earth is a very special planet in the universe. This is that little gem there, and you can see it's beautiful from space. It's just stunning. That little gem is where God himself became a man and died our death. I mean, of all the planets, that's the one where he visited.
His creation.
That's exactly right.
Yeah.
So it's quite stunning. You might notice too that the moon, the back side of the moon here that we're seeing, that's the side that we never see from Earth. It looks quite different from the near side, doesn't it? So there's the side we always see, and then we rotate it around, and there's the far side of the moon.
What characteristics differentiate?
Yeah, you notice it's much brighter. It tends to not have those dark features on it. Now, those dark features are called Maria, and that's Latin. It means seas. seas. And they used to think those were actual bodies of water, actually, but they're not. They're actually rock, basalt rock. It's just they're kind of lower places where we think in the past volcanic activity has come in, and it was liquid at one point and is now hardened into solid basalt. And the first moon landing, in fact, was in one of those Mare Tranquillitatis. But the far side doesn't have oh, that was interesting. Let's back up a little bit there. Let's take a break from that and talk about this, because every now and then when the moon is in its full phase, it will go directly behind the Earth, and that's Earth's shadow falling on the moon there. And that's called a lunar eclipse. And so you just, it takes a few hours. Yeah, it gets very dark, and sometimes it'll turn orange as light refracts around Earth's atmosphere and hits the moon. And I've seen a number of lunar eclipses, and they're very stunning.
Yeah.
And so, of course, some people, maybe you've heard some of these things about, well, you know, there's these four, they call them blood moons.
Yes.
You've heard of that? Yeah. Well, they're just lunar eclipses. Getting back to the Maria here, you can see the Maria, almost all of them are on the near side, the Earth-facing side of the moon, and the other side has almost none. And that's a little bit of a mystery. We don't know quite why that happened. My friend and colleague Danny Faulkner and some other creationist astronomers think that maybe the moon was hit with something, perhaps during the flood year. Maybe God used a meteor swarm to trigger the flood on the Earth, and a few of those hit the moon as well, because the moon's relatively close to the Earth. But they all would have happened around the same time, and since the moon rotates slowly, if they all hit the side that's Earth-facing, then that would explain why we have the Maria just on the near side of the Earth. Yeah.
So sounds like something hit that side.
It does, yeah. In fact, it's pretty much everyone agrees that these are large impacts that have been filled in with magma. Yeah. Okay, so let's move out then and take a look at some other aspects of the solar system here, and we'll center on the sun.
There's the sun.
There's the sun, and what I've done, those lines that you see, those blue lines, are the orbits of the planets, and I'm going to kind of move a little bit out of the way here so we can see those. And there you can see the inner planets. Now I've got them labeled. The labels are pretty small, but it's basically Mercury, Venus, Earth, and Mars. That's the four innermost planets. And then as we back out even further, you can see the orbits of Jupiter, Saturn, Uranus, and Neptune. And those of you that were expecting Pluto, well, he's still there, but he's no longer a planet. And so
got demoted.
That's right. We'll maybe come back to that as well. But anyway.
So go into the first four, there we are.
Yeah, so the first four, the inner planets, and you can see how much closer to the sun they orbit than the outer planets. It's not a small difference. I mean, you can take a look at how close they are to the sun, and then take a look at Jupiter, Saturn, Uranus, Neptune. They're much further out.
Right.
And you don't see that in a lot of children's books on the solar system where they have them all lined up, because they just want to give you the order. Yeah. But the scale is incredible. The distance between these worlds is really incredible. And I wanted to point out, too, that the orbits of the planets, they're almost circles, but they're not quite. You might be able to notice that the orbit of Mercury, for example, is a little bit off. It's not quite a circle. The sun's not quite in the center of that orbit. No. It's a little bit squashed. And that was a remarkable discovery that was made by a creation scientist. It was Kepler, who was he was a Lutheran, very devout Christian, and a young Earth biblical creationist. Yeah. And he discovered that the orbits of the planets are not perfect circles, but are in fact slightly elliptical.
And when did he live?
1500s, 1600s, yeah. 1600, around there. And he was concurrent with Galileo, actually, so around 1600. And he was actually discovered that they're not perfect circles. And of course, you might say, well, it's obvious. Well, he didn't have these nice computer simulations.
No, he didn't have a computer.
And so it is not at all obvious from Earth, because if you think about it, we're on one of these planets, watching the other ones move, and from that, he was able to figure out that these orbits are not perfect circles.
Do you ever lay in bed at night and think what a privilege it is as an astronomer to live when you do, to have the tools that you have?
Yes, I think of that often, actually.
Yeah.
And I think of what it would be, too, what it would mean if I could somehow travel back or bring Kepler forward in time, or Galileo forward in time, and say, let me show you about these worlds that you just saw as little points in the sky. Look at what we know about them now. It's incredible.
We really do stand on the shoulders of those who went before us, don't we?
We really do.
We're thankful for their knowledge that helps us to find new knowledge. Yeah.
Absolutely.
Yeah. I didn't mean to get you off the subject
there. That's great.
Yeah.
So Kepler, he discovered that the orbits are not perfect circles, but ellipses. And ellipse is basically a squash circle. A circle is all the points that are equidistant from one point. An ellipse is all points that are equidistant from 2 points. That is, if you add their distances from those 2 points, it's the same for all points in the ellipse.
Do we know why?
We do. But Kepler didn't.
Okay.
Kepler didn't. He just knew that they had that characteristic, but he didn't know why. It was another creation scientist. Isaac Newton, who figured out why it is that planets orbit in ellipses like that. It has to do with the nature of gravity. Newton figured out that the reason planets orbit and the reason the moon orbits the Earth is because of gravity. Gravity pulls things, it exerts a force toward the object. And so if the moon were not in motion, it would fall straight down toward the Earth, but the moon has kind of a sideways motion. And so it would just go this way, except Earth's gravity pulls it down into a elliptical orbit. And Newton figured out that there are three possible types of orbits based on the nature of gravity. Orbits can be either, they could be a perfect circle, theoretically. I mean, if God had started the moon with just the right momentum, it would orbit in a perfect circle. But if you start it with a little more or a little less, it'll go into an elliptical orbit. And if you start it with too much, it'll go into a parabola or a hyperbolic orbit where it never actually, it's not a true orbit because it never comes back. It'll actually just launch out into space. Yeah. But that's the shape that's allowed. So parabola, hyperbola, which are similar. Hyperbola is more open. And then an ellipse or a circle. A circle is a special case of an ellipse.
So are you saying there's some design to this?
There's a lot of design to this.
Yeah, there is.
And in fact, the force of gravity has to be just right in order for orbits to be closed like that. It turns out that the gravity falling off as r squared, which is exactly what gravity does, makes the orbits ellipses like that. So it's rather remarkable.
We've got to take a break. This is fascinating, and I'm sure there are folks out there just learning and having a wonderful time tracking with you. So don't you go away, and don't you go away. We'll be right back. We are back with Dr. Jason Lisle, and we've been just kind of giving an overview of the solar system. We've been talking about the moon and about ellipses. So pick us up where we left off, friend.
Okay, well, it was a creation scientist. And by the way, I mentioned that because people think, oh, you can't be a creationist and do science. Well, actually, some of the bigwigs of the past who made major discoveries were biblical creationists, very devout Christians. Kepler, in particular, a very devout Christian. And in fact, I know he was a young Earth creationist. He actually did his own calculation along the lines of Bishop Ussher, and he got a slightly different result, but it was about 6,000 years, something like that.
Wow.
And he discovered, based on data that had been taken by Tycho Brahe, who was sort of his predecessor, their lives overlapped. Well, there was 1 year where they worked together, and then Tycho died and bequeathed his data to Kepler. And they didn't have telescopes at this point, keep in mind. But Tycho, what he was using various devices where he could measure the positions of the planets very, very precisely. And from that data, Kepler was able to, using math that is really quite complex. Again, it's easy because we can, with software, we can zoom out and look at the solar system from above and we can say, oh, of course the planets orbit in ellipses, But it's much harder when you're on one of those specks and you're watching the other ones move, and you have to compensate for your own motion, which you don't really know. It's really remarkable he was able to figure that out. So one of his discoveries was that the planets orbit in ellipses, and remember the ellipse is all the points that are equidistant from 2 points, and these 2 points are called foci. Each one is a focus. And he also discovered that the sun is always at one focus of the ellipse, the other one's empty. Don't ask me why. It's not, I can't give a short, simple answer to why the math works out that way. I'm not sure Kepler could either. He didn't even know why that was the case, but he did know that planets orbit the sun with the sun at one focus. And you can see that with Mercury's orbit. If I zoom in here a little bit, you can see that Mercury, one aspect of its orbit, it's actually much closer to the sun at some points than it is at others. If I watch it orbit here a little bit, in fact, let me highlight Mercury so it'll turn that orbit red there so you can see that. So Mercury's in red, and you can see that it's closer to the sun right there. And then if I speed up time, it gets further away from the sun right about there. It's not a huge difference, but it is a little bit squashed. And Earth's orbit's that way as well, and so is Mars. In fact, you can see Mars sometimes, because both its orbit and Earth's are squashed, sometimes Mars is much closer to Earth's orbit than it is at other times. And in fact, let me speed up time here, and we can actually see that. You can see Mars comes very close to the Earth's orbit right about there. Mm-hmm. And then if I let it go a little bit longer, you can see it's further away there. And so sometimes when Earth makes a pass to Mars, sometimes it makes a real close pass because they happen to be, like for example right there, that's a pretty close pass, isn't it? Earth and Mars, yeah, it's pretty close to the way it gets. And then, but it can also be a little bit further away as well. And so it just depends on where it's at. But Kepler also found that planets that orbit closer to the sun, their period is much shorter. You can see Mercury is really whipping around there. It takes only 88 days for Mercury to orbit the sun once. It takes the Earth a year, and the outer planets are even slower. In fact, let me zoom out here, and you can see Mercury is really whipping around there. But as I zoom out, Jupiter and Saturn, barely moving. Uranus and Neptune, barely moving. And so that was another thing that Kepler figured out. He figured out the exact mathematic relationship between the distance that a planet orbits from the sun and its period. And it turns out it's a rather simple relationship. It's the period squared is equal to the distance cubed.
Wow.
Isn't that interesting? And
Yeah.
so it seems like there's some design in there as well.
Absolutely.
That it obeys that particular relationship. Again, Kepler didn't know why. It was another scientist, a creation scientist, Newton, who figured out, well, that's because gravity. Gravity's pulling more strongly on Mercury because it's closer to the sun. And so it really gets whipped around there. But the other planets are probably slower.
Further out, the less gravity.
Yeah, there's less gravity. You're feeling less force from the sun, and so it takes less to deflect that orbit. So it just orbits much more slowly.
Yeah.
And then finally, he also noticed that planets within their orbit, when they're closer to the sun, they tend to speed up a little bit. So you notice Mercury. It's a little hard to see with Mercury, but you can see it's a little faster right there when it's close to the sun than it is when it's further away.
Sure.
Now the best way to see that actually is with comets, because planets are all sort of pretty close to circles, and they all orbit in roughly the same plane, as you can see there. All the planet orbits are pretty close to the same plane. But comets obey neither of those little generalizations. And so if we take a look at comets here, let me turn those on, we can see that the orbits of comets tend to be very elliptical, and they really go pretty far out. And they're also not necessarily in the plane of the solar system. You can see comets kind of do what they want. It's been said that comets are like cats. They have tails and they do what they want. So I think that's a good analogy.
Right.
So let's highlight Halley's comet here, which orbits backwards from the planets, interestingly. Some comets do that. And if we speed up time here, you can see that Halley really whiplashes around the sun like that. It's slow when it's further away, as it is there, creeping around. Let me speed up time here a little bit, otherwise it'd take forever. But you can see as Halley falls closer to the sun, it just whiplashes around like that. Yeah. That's because the sun's gravity. Yeah, it's
sucking it in there.
Exactly.
Yeah.
It's really pulling on
The
it.
closer it gets, the more it pulls it in.
Right. So that's Kepler's, that's actually his second law that he discovered, is that planets and comets sweep equal areas in equal times. Basically, it means that they speed up when they get closer to the sun. So those three laws of planetary motion were all discovered by a creation scientist. How about that?
Yes, that's awesome.
Now, there are other objects in our solar system, too, that people forget about. For example, asteroids, and let's take a look at some of those. Asteroids basically are minor planets. I'll turn on the dwarf planets as well. But there are more objects that orbit the sun than just the planets and just comets. There are asteroids, which are basically minor planets. In fact, that's one of the terms for asteroids. They're a planet, they're just smaller. And the first asteroids, when they were discovered, were classified as planets. How about that? There was a time when there were 11 planets in our solar system. Did you know that?
It's an arbitrary call, isn't it?
It is a little bit, yeah, because who decides what's big enough to be a planet?
Right.
There are thousands of asteroids. There are at least 7,000 that have a name, something like that. And of course, that would be a lot of planets for kids to memorize. So we decided it has to be a certain size to be called a planet.
Got to get it down to what sixth grader can memorize.
Exactly, exactly. And so there you can see this. But the first 4 asteroids, when they were first discovered, this was before Neptune had been discovered and before Pluto had been discovered, they were actually classified as planets. And then later, as we started finding more of these things, they were demoted. And that kind of reminds us of something else that happened recently. What was once a planet, Pluto, a similar thing happened. As we started finding other objects like Pluto out there that are about the same size, we realized we're going to have to add hundreds of new planets to the solar system or demote Pluto, and it's much smaller than these other worlds.
So that's what we really discovered. There were other ones that were just as big, and if we weren't going to recognize them, we couldn't recognize Pluto.
Exactly, and one's bigger, so we'd either have to add a bunch of new planets or demote Pluto, and it made more sense to demote Pluto.
So you agree with that?
I think that's probably the right call. Yeah.
Okay. All right. Well, how would you pull this together?
Well, I'd say we see a solar system that has incredible evidence of design. Everything's working together. Everything's obeying these mathematical laws that human minds are able to discover using mathematics. That's kind of the language of God, really. We've seen that creation scientists were largely responsible for a lot of these discoveries. In fact, the ones we talked about today, it was all creation scientists who discovered these things, devout Christians. And we see that the universe declares God's glory. It's designed to do what it does, and it does it very, very well.
You know, the universe and the solar system haven't changed. They're exactly the same as they were when Kepler was working.
Yeah,
what has changed is our assumptions today.
Yeah, that's right.
And we've wanted to forget God.
Yeah.
but you reminded us that God was whispering in the ear of the great men ahead of us who discovered these things and on whose shoulders we stand.
That's exactly right.
That's a great thing for us to remember. And it's a great thing for all of us, but especially for our young viewers, to know that they can believe in God and study science. And science is never going to contradict God because He thought of it.
That's exactly right.
Yeah. And I'm so thankful for you. You're a great role model to those young men
Thank you.
and young ladies out there. My friends, we've just been looking at the solar system today, and we've been looking at the order of it and the design of it, and we've been looking at how God has used creation scientists throughout the ages. We've had a great one of them with us today, and I hope that through his teaching today, you have come to be reaffirmed in the fact that it's God's view that He created you. That should always be your worldview too. Hope we'll see you again soon here on Origins. And until then, God bless you, my friend.
Thank you for watching this edition of Origins. If you'd like a copy of the PowerPoint information presented today, you can download a PDF file from our website at www.originstv.org. Or for a DVD of this series, you can order online or send a $12 donation to cover shipping and handling and write to Origins Program Number 1501, Cornerstone Network, Wall, Pennsylvania 15148.
Origins is made possible by the faithful prayers and financial support of you, our Cornerstone family.